Dear students, good morning. Again, I welcome all of you in today's online class. In today's online class, we will discuss an important topic, Meson theory of nuclear forces. So, any attractive force between two particles is regarded as the exchange of an attractive property. As we have studied in junior classes, charged particles are surrounded by electromagnetic field. Similarly, we may introduce a new kind of field known as nuclear field surrounding each nucleon. The application of quantum mechanics to the electromagnetic field surrounding a charged particles leads to the conclusion that the electrical force is exerted by the transfer of a photon, which is referred to as the field particle of the electromagnetic field, from one charged body to another. Japanese scientist Yukawa in 1935 thought that the strong interaction between nucleon might be accounted for in a similar manner by postulating an appropriate field particle of rest mass different from zero. This virtual particle has been given the name Meson to show that the range of force is related to the mass of exchange particle. Assume that the pi0 meson is contained virtually in a photon. A temporary dissociation would be allowable if it doesn't take a time longer than delta t, given by the uncertainty principle. Delta t equals to h cross upon delta E. Here delta E is equals to proton mass plus pion mass into c square minus proton mass into c square equals to pion mass into c square. Or you can say this is the energy, the difference of mass which is converted into energy. If this virtual particle travels with the velocity of light as might be expected for a field particle, then the greatest distance the meson could travel in this time, also known as range of the pion exchange force, that is capital R is equals to C delta T, which again is equals to H cross upon M pi into C. Based on non-nuclear dimensions, Yukawa assumed that the range of the Nucleon force and of the field particle would be about 2 into 10 to the power minus 15 meter, and this led to a value of pion mass roughly 200 times the mass of an electron. About 2 years after Yukawa's theory, particles of mass about 200 electronic mass were discovered in cosmic radiation. These virtual particles are now known as mesons, which were thought to be Yukawa field particles for more than 10 years. Several different mesons with different charges and rest masses have been discovered. It was found that the Yukawa particle was not the mu meson but its parent, the solder left by Meson. The pion, which occurs in positive, negative and neutral forms, has a mass about 270 times that of the electron and interacts very rapidly with matter. It has other properties, spin and parity, which qualify it to be the field particle for Nucleon forces. The attraction between any two nucleons could arise from the transfer of a pi0 meson from one nucleon to the other. The force between a proton and a neutron could result from the transfer of a pi plus meson from former to the latter, or of a pi minus meson in the opposite direction, that is from neutron to proton. To interpret the nucleon scattering data in terms of a potential function, let us compare the Meson theory with the quantum theory of electromagnetic interactions. To obtain a pion wave equation, we express the total energy E of a pion in terms of the pion rest mass energy m pi into c square and momentum p as E square equals to p square c square plus m pi square c square. The energy E and momentum component P are represented by the operators E equals to IH cross del upon del T, X component of momentum Px equals to minus IH cross del upon del X, Y component of momentum Py equals to minus IH cross del upon del Y, and Z component of momentum Pz equals to minus IH cross del upon del Z. Introducing a pion wave function phi, which is a scalar function, we obtain the Kg equation for a free particle of spin 0, that is minus h cross square delta 2 phi upon delta t square equals to minus h cross square c square Laplacian phi plus m pi square c raised to power 4 into phi, or it can be written as Laplacian phi minus 1 upon c square delta 2 phi upon delta t square minus m pi square c square upon h cross square into phi equals to 0. From m pi equals to 0, that is, if pion mass equals to 0, it reduces to the well-known wave equation Laplacian minus 1 upon c square delta 2 upon delta t square into phi equals to 0. For the quanta of the electromagnetic field, the simplest type of electromagnetic field is the electrostatic field, where del phi upon del t equals to 0. The corresponding static pion field is the analog of Laplace equation in the absence of electric charges. The presence of charge requires the analog of Poisson's equation Laplacian phi equals to E rho upon epsilon 0, where E is the magnitude of the electronic charge and rho is the electron particle density. In our present case, we have nucleon charges interacting with the pion field. For a static pion potential due to a single point nucleon charge G at the origin, we have the equation Laplacian phi minus m pi square c square upon h cross square into phi equals to 4 pi g into delta r. The solution of this equation, which vanishes at infinity, is phi r equals to minus integration of e raised to power minus mu into magnitude r minus r dash into g delta r dash delta tau dash divided by magnitude r minus r dash. Here mu is approximately equals to m pi c upon h cross and d tau dash is the volume element. If we have a point source of strength G at R1, then we have phi r equals to minus G e raised to power minus mu into magnitude r minus r1 divided by magnitude r minus r. So the potential energy of a source G at R2 in this field is given by V equals to G into phi R2. If the potential phi is due to another source G at R1, then the interaction energy between two sources is capital V equals to minus G square e raised to power minus mu multiplied by magnitude R1 minus R2 divided by magnitude R1 minus R2, which again equals to minus G square e raised to power minus mu into R divided by R. Comparing with the relation for Coulomb potential, we see that this nuclear potential decreases more rapidly with distance from the source than the Coulomb potential by an exponential factor. At separations small compared to mu raised to power minus 1, this potential energy varies with R just as the Coulomb energy loss. Yukawa noted that this interaction energy may account for the fact that nuclear forces act only over a short range and that the range capital R is equals to 1 upon mu, which again equals to h cross upon m pi into c. Substitution of the value of m pi as 270 electron mass me gives capital R equals to 1.4 into 10 to the power minus 15 meter or 1.4 Fermi, which agrees with the observed range of the nuclear forces. Since in this theory the nuclear particle doesn't change its charge, we find that according to the theory, neutron-neutron, neutron-proton and proton-proton forces are equal. So that's all in today's online class. Thank you.